So we're going to have a quick little overview of Gibbs Free Energy. What we've talked about already in class is exactly what Gibbs Free Energy is. Gibbs Free Energy is simply a measure of the uh, the temperature times the change in entropy of the universe. And we know from what we've talked about already is that all spontaneous processes must be accompanied by an increase in entropy in the universe. So not just increase in entropy, but an increase in entropy in the universe. So when we end up with situations where we have a decrease in entropy, like this equation here, 2 moles of sodium with a mole of chlorine gas giving 2 moles of sodium chloride solid. This is clearly a decrease in entropy because we see that we have gas going to a solid and we have 3 moles going to 2. So that increase in entropy can be quite a problem for some people. Now, because we are allowed to have um, this statement, so the entropy of the universe is equal to the entropy of the system plus the surroundings. What that means is that if the entropy of the system is down, then the entropy of the surroundings must be increased by a lot. So when we see equations where we see a general decrease in the amount of entropy, we generally find that those reactions are highly exothermic to counteract for that. So an equation was created at the turn of the last century basically to look at how these changes were taking place and to make predictions on whether or not a reaction would proceed under normal conditions. So we call this Gibbs free energy, and what we basically get out of it is that when delta G is less than 0, we say the reaction is spontaneous or thermodynamically favored. When delta G is greater than 0, we say it is not thermodynamically favored or non-spontaneous. And if delta G is equal to 0, we say the reaction is at equilibrium. So the whole purpose of this, or the whole driving force, is that a reaction will always move in the direction that minimizes energy. So what that looks like here is that in the forward direction of the Haber process, which is what's outlined up here, the reaction will proceed until this low point, where we would say that delta G is equal to 0. But if it continues past the center point, it will actually operate in the reverse to get back there. So it's always going to be moving back towards that valley. So we end up with the ability to use this equation easily and frequently. So it says free energy is equal to enthalpy minus T delta S, or the entropy times temperature, the absolute temperature. So delta G in this case, it says calculate the standard free energy of formation, and it gives us delta H and delta S. So we're just going to plug it in. You'll notice that the units on entropy are in joules per Kelvin, and we need it to be in kilojoules. So we can go through and actually calculate that. So 180.7 take away 298, 0.0247 is 173.3. So delta G is greater than 0, so this is non-spontaneous. In other words, there will be no increase in the entropy of the universe, therefore it's not going to work. Next up, we can use Hess's law to actually do this as well. So we can always use the appendices in the back of your textbook to do these calculations. So we have P4 gas going to 6 moles of chlorine to 4 moles of PCl3. So the standard Gibbs free energy change is equal to 4 times the free energy change of PCl3 minus 6 times the free energy change of Cl2 minus the free energy change of P4. So the free energy change of elements in their standard states is equal to 0. So those two are actually equal to 0. So delta G in this particular case is just equal to the free energy change of PCl3. So we go and we find phosphorus, list it, PCl3 gas, so it's right at the bottom of the sheet, and we find a free energy change of negative 269 equals 4 times negative 269.6 kilojoules per mole. And we will actually see that chlorine, where is it? Chlorine is 0, and we can check phosphorus for solid. Oh, it's not solid, it's gas. Phosphorus for gas, and it's 24.4. So we go through and we complete that calculation. So 4 times 269.6 negative, take away 24.4, delta G standard state is equal to negative 1102.8 kilojoules, or negative 1100 kilojoules for significant figures. So part B of this simply asks me what the free energy change of the reverse process is. So delta G of the reverse would be equal to plus 1100 kilojoules. It's got to be balanced, right? So that's essentially what we're doing, Hess's law, and then we can find out the reverse. So free energy and temperature is kind of an important idea. We have two terms in this Gibbs free energy calculation, which one is the enthalpy term and one is the entropy term. So remember, enthalpy is heat of reaction, entropy is the degree of disorder. And the free energy, or whether or not a reaction takes place, is based on a combination of those two terms. If we know the signs of those two terms, which is what this table is indicating, we can actually make a lot of predictions on when the reaction will be spontaneous or when it will be thermodynamically favored. So if the enthalpy term is negative and the entropy term is positive, it will be spontaneous at all temperatures. If the reverse is true, it will be non-spontaneous at all temperatures. If both terms are negative, it will be spontaneous at low temperatures, but as it heats up, it will become non-spontaneous. If both are positive, they will be spontaneous at high temperatures, but more spontaneous as it cools off. So let's have a couple little looks at what that would mean. So it says the Haber process, so N2 plus H2 is in equilibrium with NH3, 2, 3. So it says, what is the standard enthalpy of formation of this? I'm assuming it's of this particular reaction. So we can go to ammonia and see its free energy is, enthalpy is negative 46.19 kilojoules per mole. The condition that we have here is that it's actually times 2 moles. So 46.19 times 2 equals negative 92.38 kilojoules. So we have a negative enthalpy. It's exothermic. So the standard entropy of formation. So the standard entropy of formation is equal to the entropy of ammonia times 2 minus the entropy of hydrogen times 3 minus the entropy of nitrogen. So entropy doesn't really have zeros for the pure elements, so it becomes a little bit, you actually have to do more calculations than that. So the entropy of ammonia, so we flip through our guide here. The entropy of ammonia is 192.5 joules per Kelvin. And we've got to multiply that by 2. minus 3 times hydrogen, (130.58) minus nitrogen, 191.50. These are all joules per Kelvin. So we go through and do those calculations. So 192.5 times 2, take away 3 times 130.58, take away 191.5, and we get negative 198.24 joules per Kelvin. So using the table above, predict the sign and predict what's going to actually happen as we increase temperature. So both terms are negative. So it will be spontaneous at low temperatures and non-spontaneous. So it should become non-spontaneous. At what temperature will the reaction become non-spontaneous? So delta G is equal to delta H minus T delta S. So non-spontaneous, we want to know when this is equal to 0. T delta S is equal to delta H. T is equal to delta H over delta S. T is equal to negative 92.38 kilojoules over negative 0.19824 kilojoule per Kelvin. We do that calculation. 92.38 divided by 0.19824 equals 466 Kelvin, or 193 degrees Celsius. This reaction will become non-spontaneous. So now we're going to have a look at free energy and the equilibrium constant. So we know that delta G is equal to 0. That means the system is at equilibrium. But we're now going to start moving to what we call non-standard conditions. So before we can talk about non-standard conditions, we have to actually define what standard conditions are. So standard conditions are pure solids and pure liquids, which don't really affect equilibrium anyway. But gases have to be at 1 atmosphere of pressure and solutions have to be 1 mole per liter. A solution can start out standard and then become non-standard very quickly. So non-standard really is what most reactions will actually be. And elements have a standard state of 0, which makes life a lot easier for a lot of calculations. So we are simply going to correct the delta G expression with this plus RT ln Q, where Q is the reaction quotient, R is 8.314 joule per mole Kelvin, and T is the temperature in Kelvin. So what we're looking for here is we are looking for an ability just to figure out exactly what free energy is. We can calculate free energy and predict it to be spontaneous, but if the conditions are not standard, that means that we could be very wrong. So before we get too far, we're going to have a quick look at this particular reaction. As we saw earlier in our course, the normal boiling point of the temperature of a pure liquid is when it's in equilibrium with its vapor at 1 atmosphere, whatever the atmosphere is at that point. So to write the boiling point expression, we have a liquid in equilibrium with its gas. So we can calculate the delta G for this. Delta G standard is equal to the delta G of CCl for gas minus the delta G CCl for liquid. Delta G, so we look to appendix C. So CCl4, we're starting with gas first. So negative 64.0 kilojoules minus 68.6 kilojoules. That's a negative. So we do our calculation, 64 minus take away 68.6 minus delta G equals plus 4.6 kilojoules. So we know that we have a very, very slight non-favored reaction. So the question now is what temperature will this boil? So we know from just a minute ago that delta H over delta S will give us the temperature. So in order for us to calculate what temperature this will actually boil at, I know it's not part of the question, but it seems to become pretty relevant here, is all we have to do is calculate the enthalpy of each one. So on the top, we'll calculate the enthalpy. So the enthalpy for this will be, it's going to be gas take away liquid. So negative 106.7 take away negative 139.3. And the entropy will be 309 take away 214.4. So we can do our calculations now. So 106.7 negative, take 139.3 negative, equals 32.6 endothermic, which is what we would expect boiling to be. Take away 309, take away 214.4. Times 1,000 is 344. So all I'm doing there is 344.6. All I did there was take into account that I hadn't converted this from joules. So these should be 0.309 take away 0.214, sorry. And 344.6 take away 273 is a boiling temperature of 71.6 degrees Celsius, which is the boiling point. It's a very, very useful calculation to be able to do. So now we're going to try and apply that expression we were just looking at. So we have non-standard conditions because this is not 1 atmosphere. So we're going to figure out what delta G is at non-standard conditions. Plus RT ln Q. So before we do anything, we should probably calculate what the free energy should be. So we're going to calculate delta G first. Delta G is equal to 2 times the delta G of NH3 minus 3 times the delta G of H2 minus 1 times the delta G of N2. These are both 0. So delta G is equal to 2 times ammonia, negative 16.66. 16.66 negative times 2, negative 33.32 kilojoules. So now we're ready to go. So delta G non-standard is equal to negative 33,320 joules plus 8.314 times 298 Kelvin, and this is joule per mole K, it's the unit on 8.314, times the natural logarithm of the reaction quotient. So in this case we have PNH3 over PH2, PN2. Make sure we get our exponents in there. PH2 is 3. So for ammonia we have 0.5. For hydrogen we have 3. And for nitrogen, we have 1. So we're just going to plug those variables in from up here. So delta G is equal to negative 33,320 joules plus 8.314 joules per mole K times 298 K. So let's do our calculation. So concentration of ammonia squared divided by the concentration of hydrogen cubed times 1 is the natural logarithm of 9.26 times 10 to the negative 3 ln times 298 times 8.314. Plus negative 11600. K cancels. Joules. Delta G is equal to negative 44,920. Delta G is equal to negative 44.9 kilojoules. That is the non-standard free energy. So if we set delta G equal to 0, which is this is what we need for equilibrium, we can change Q to K. So then we can rearrange and actually solve for K, so we can get an expression for K. K is equal to E to the negative delta G over RT is equal to the E to the negative 33,300 joules per mole over 8.314 times 298. So we got our negative there, but delta G is negative, so we gotta make sure we have 2 negatives there to make it positive. So we do our calculation, 33,300. So negative then negative, divided by 8.314 times 298. So it's equal to E to the 13.4406. K is equal to 6.87 times 10 to the 5. There's your equilibrium constant.